Hello, welcome back to all my amazing students. I hope you guys are having just a great day today. I hope you had a nice, restful weekend. Hope you did something cool and fun. I know I did. We went up to the shuttle launch and saw the SpaceX craft take off, so that was pretty awesome. Um, had a nice, relaxing time. Went to Disney Springs afterwards. Of course, we had our masks on. We were nice and social distanced. It was fun. So anyway, we're gonna go ahead and dive right in. We're gonna start our next topic here. This is actually going to be two topics in one tonight because we are going to pick up the pace a little and really start to knock some of these topics out, especially the ones that, I don't want to say easy is not the right word, but topics that don't take too long to cover, don't have a lot of content in them. We can just kind of tick some extra things off with every class that we go through, and you guys will be able to progress even quicker through your essential ed. So, without further ado, let's get going. So, tonight's lesson is topics 4 and 6 in level M. That's M as in Mary. By the way, my webcam is not working for some reason, so that's why you can't see my face. Sorry, I'm still investigating how to fix that, but I will get it working soon. Anyway, this is level M, topics 4 and 6. Topic 4 is about measurement, and then topic 6, we start to talk a little bit about geometry in terms of things like lines and angles. So let's do topic 4 first. That's going to be about measurement. We use the idea of measurement to measure all of the things that are observable in our universe. So we can measure the length of an object, we can measure its weight, we can measure its volume, which is how much it can, like how much material can fit inside the space of the object. There's just so many things we can measure. We can measure time, even though time is not necessarily observable to the naked eye. It's something that you can feel the concept of time passing, and therefore it's something that we can measure. So when we talk about measurement, we use the term units, and units is like a very widely encompassing term. So because units is like the increment or the measurement that we use to measure something. So, for example, you measure time using minutes, or you can measure the length of an object using inches, and those are the units. So there's two very important skills that we have to understand about the concept of measurement. One is like the practical application, which would be converting between different measurements. This is something that you have to do like on a daily basis. Doesn't matter what your profession is. If if you're a stay-at-home parent or an architect or a construction person or just anything, there's just unit conversions happening all the time. Probably the one that's most common would be like measuring the time of something. So we're going to talk about how to do converting between units. And then I didn't really make a notes section about this, but the idea of choosing the best unit to use, that's just sort of about being able to envision in your head what an object looks like, and then what type of unit you should use to measure whatever it is you're measuring about it. So, for example, you might have something like, a bookshelf or a piece of furniture, of a sofa or a desk or something, and so you might look at that and you might want to use like a standard measurement like feet maybe to measure that, because there's several feet in the width or length of like a sofa or a piece of furniture. You might use inches, and that just depends on how you are purchasing it, because a lot of times when you buy things like furniture, if they're not huge pieces of furniture, they might tell you the measurement in inches. But if you were going to buy something like, um, I'm just looking around my room to see some examples here that I can lend myself to. Let's say that you're buying a picture for your wall, um, or like a picture frame to put a picture in. You might look at that type of measurement definitely and certainly in something a little smaller than feet, like inches. In other words, it wouldn't necessarily be to your advantage to use feet because a foot has 12 inches in it already, so it's just a quicker way or more efficient way of breaking down a measurement of a longer object. But a picture frame typically doesn't span larger than the measurement of inches. So feet would not be a great thing to use there, or anything larger than that, like yards. You wouldn't want to use yards for that either. So that's all I mean by choosing the best unit. It's just about envisioning the object and thinking about what would be the best unit for you to use for that. So before I talk about dimensional analysis, in this notes document, which I posted for you on Google Classroom, on the second page, I actually have this amazing chart that you can use to show different units, whether they are in American, that would be this side, or we also call it like US for United States. And then you also have metric, which is on the other side. The systems are different. In the United States, we typically talk about things in terms of things like feet and yards, miles. We talk about the capacity of something or its volume by talking about that measurement being in gallons or quarts. When you go to the grocery store, you don't buy, milk necessarily in terms of liters or milliliters. Instead, you buy a gallon of milk, and a gallon is a United States or customary American measurement. We also talk about weight in American unit system of measurement in terms of pounds and tons. That's a United States thing. And we also use Fahrenheit in terms of temperature. Those are just some units that are standard to the United States. Then you also have metric, and metric is used in the majority of the rest of the world. In length, instead of using things like feet, yards, and miles, we use centimeters, decimeters, meters, kilometers. And the whole idea behind the metric system is that it's based on tens. So if you're interested in knowing a little more about that, I can send you a chart that shows you how you break down the meters basically. So in the metric system, they use meters as like the base measurement. And then if you notice something about all these measurement units that you see here, the meter part is part of every one of these words, okay? The only thing that's different is the prefix, centi, milli, deci, kilo, and those mean different things depending on that placement in the metric system. So there's a chart that you can look at, and in some ways the metric system is a little easier to remember because everything is in meters and for length, for example, and you just need to remember what's the difference between centi, deci, kilo, etc. And rather than the American system where you have to literally remember the placement of, is a foot longer than a yard, is a yard longer than a mile, etc. In the metric system, we use liters to talk about the volume or capacity of something, and we use grams to talk about the mass or the weight of something. And again, in liters and grams, you would just add the appropriate prefix depending on what you're referring to, whether that be centi or milli or kilo, etc. In metric, we'd use Celsius to talk about temperature. And then in the middle of the bottom here, this is where I'm going to be going for some of the examples. In the middle here, we have a conversion chart where you can compare the metric measurement with the United States measurement. So, for example, if you think about the speedometer on your car, those measurements are in the United States, we care about miles per hour because everything is in miles per hour. because miles is a measurement of distance. Here's miles right here. Measurement is a distance. Miles is a measurement of distance in the United States, and in other parts of the world, like the UK, for example, they would use kilometers instead of miles, and there is a conversion for that. It is right here. So for every 1 mile, there's 1.6 kilometers in that mile. And it's just a variation based on how it's measured. But that's one example that you can think of. And the reason I brought up the speedometer is because I think almost every car nowadays on the speedometer, when you look at that, it has miles per hour, and then it also has kilometers per hour. And the scale is different, and that's because the length of a mile is actually shorter than the length of 1 kilometer. So, just a little tidbit, fun fact for you. We're going to do some example problems now for converting. There's a really big fancy terminology that you can use to explain what converting is. And in science, we call it dimensional analysis. And if you think about that, that makes sense because you're comparing or converting the dimensions, based on different units. So that's where we get that terminology from. And there's a process you can follow every time. It works every time. You only need to know the conversion factor. So that's the thing I have in bold right here, conversion factor. So what's a conversion factor? Well, a conversion factor tells you how much of something, we'll call it A, is in something else, so B. So a really good example of a conversion factor could be there's 60 minutes in every 1 hour. Okay, and that's the gist of what a conversion factor is. You can express that in different ways. Another way to express that would be in every hour there are 60 minutes. And when would you use one versus the other? It all depends on what the problem is that you have in front of you and what it is asking you to solve. So I'm going to switch colors here. We're going to go to question number 1. A sign on the highway tells you that the next exit is 45 miles away. So how far away is that in feet? So we are going from miles, which we have, to feet. So in order for us to figure this question out, we need to know how many feet are in a mile. And the way we're going to do this is we're going to put the thing that we are starting with here, which is 45 miles, and we're going to multiply that by a conversion factor. Now, what you always want to do when you're doing dimensional analysis or converting the units is the thing you're trying to get rid of or change away. We don't care about miles anymore. We want to know feet, so we're trying to get rid of the miles. You want to put that down here on the bottom of your conversion factor, because when you multiply this, the miles are going to cancel out. And I'll show you exactly what I mean by that once we get what these values are. So if miles is on the bottom, that means that feet has to be on the top. So we need to know in 1 mile how many feet are there. And we can do that by going to our conversion chart. In 1 mile, there are 5,280 feet. So we need to go and put 5280 up here. And now when we do this multiplication, I'm just going to erase this because it took up too much space. When we do this multiplication, right, this miles is going to cancel out. And we just need to do 45 times 5,280. And then technically you're dividing it by 1, but something divided by 1, just comes out to itself, so you can kind of ignore that. But 45 times 5,280 is some value that I can't do in my head, so let me just calculate that real quick. It's 237,600, and the unit you have left over would be feet because the miles cancel it out. So that is what you are trying to do here. That is the goal. The thing you want to get rid of needs to be on the bottom of that conversion factor, and the thing you're trying to change it into is what's going to be left on the top. So let's apply this skill and do question number 2. You go to the store, you buy 3 bottles of soda, and each bottle has 1 liter of soda inside of it. So in total, you have just purchased 3 liters of soda. So how much liquid is this if you were to take that measurement into quarts? Okay, so if we go down to our chart here, okay, we need to find liters. Okay, here's liters, and then we also need to find quarts. Well, quarts is over here, so we have a little issue because liters is a metric unit, and then quarts is a United States or American unit, and so what we really need here is we need someone to tell us what is the conversion already between those. It's not going to be something where you can kind of engineer it yourself and figure that out. You need to actually look for something in the chart. So we do have a liters and quarts conversion factor right here. In every 1 liter, there is 1.06 quarts. Now that's approximate, okay? That's what this little squiggly line here, this tilde means, this double tilde sign. That means approximately. And so, I mean, it's fine. We're just going to use 1.06, but just know that that measurement is approximate, okay? And the reason for that is because they're in 2 different unit systems of measurement. So we're going to roll back up here, and we have 3 liters. And we need to, oops, not equals, we need to multiply that. Whoops, let me erase that. We need to multiply this. We need a conversion factor where liters is on the bottom. And so in this case, I want to know, I'm going to abbreviate quart, how many quarts are in 1 liter, and that would be 1.06, which we just learned from our chart. They told us here that in every liter there's 1.06 quarts. So I'm going to roll back up here. The liters cancel out, and then we just need to do 3 times 1.06 and put our result in quarts. And that is going to give us 3.18 quarts. I think quarts is QTS if you abbreviate it QTS. Yeah, it's quarts, 3.18. So I wrote it out and I abbreviated it. Whatever you're more comfortable with, you check that out. Okay, I want you to try this next problem on your own. We are doing a muffin recipe. We're baking some muffins. The recipe calls for 3 cups of milk. That's going to be some really liquidy muffins, I guess. Or we're making a really big batch. I don't know. A muffin recipe calls for 3 cups of milk. And how much milk is this in gallons? So this is actually a really good real-life example because you might have a recipe that you're making and you have no milk in the fridge, and so you need to know when I go to the store, how much milk do I have to buy, because milk is sold in gallons. I can't go to the store and say, may I please have 3 cups of milk? They just don't do that. So this is a good example. I want you to set the problem up and then figure out what the conversion is between cups and gallons, and then let's see if we can process that answer. Okay, great. So let's put down what we have. We have 3 cups. And that conversion factor we need to multiply by needs to have cups in the bottom. Okay. And so we need to go and find, and gallons is on the top, what's our conversion factor with gallons and cups? Okay, so do I have one that's already given to me? Of course not. So let's do some reverse engineering here. So here's where we're looking. We're over here where it says capacity. This is an American measurement because it's gallons and cups. And in a gallon, there are 4 quarts. And in every quart, there are 4 cups. So how many cups would that be that are inside of a gallon? That would be 16. So for every 1 gallon, I have 16 cups. Okay, so let's go ahead and we will cancel our cups out. And then we're going to do multiplying across the top and then dividing by the bottom. So 3 times 1 is 3. So 3, and then that's divided by 16. Okay. Now there's 2 approaches here. You can leave it as a fraction if you would like to. That would be 3/16 of a gallon. Or you can go ahead and you can actually divide 3 divided by 16. And you get 0.1875 gallons. Okay, so how does that information help us? So remember the anecdote I gave about going to the store to buy milk. Um, if you're talking about 3/16 of a gallon, that would be less than 1 gallon. Okay. Now I have a trick question for you. What if I just is there 3 cups in half a gallon of milk, like a half size? The answer to that would be yes, because half of the cups in 16 cups being in a gallon would be 8 cups, and you only need 3 of those 8 cups. So a half gallon would work also. And you can also look at this using the decimal. That might be a little easier to sort of think about, um, because you don't even have a whole gallon here. You only have 3 cups, and that's less than a gallon. Okay. Um, all right. So let's work on our last question here. You're buying a bookshelf. You measure the space that you want to put the bookshelf, and you decide that you can get a bookshelf that is 30 inches wide. If you get one that's any bigger than that, it's not going to fit in the spot you want to put this bookshelf. Go to the IKEA website to look for your bookshelf, and all the measurements on there are in centimeters. If the bookshelf you really like is 80 centimeters wide, will it work? Okay, so this is a totally different way than to ask this question. They're not just, saying convert this from this to this. They're actually asking you, if the one you want to buy is 80 centimeters, does that fit into a 30-inch space? So what we can do here is we can convert 30 inches to centimeters, and then we can decide if 80 centimeters is bigger or smaller than that. So we need to take our 30-inch measurement right here and do a multiplication. We need to have our inches on the bottom, and we're changing it to centimeters on the top. And if I go downstairs here, down to my chart, I'm looking for inches and centimeters. Here it is, inches and centimeters. So in every 1 inch, there are 2.54 centimeters. So in every 1 inch, there are 2.54 centimeters. Okay, so we will multiply. The inches cancel out. We have 30 times 2.54, and then you divide that by 1, which will just be itself. So 30 times 2.54, this is 76.2 centimeters. Now, let's think about what the question told us. Okay, 30 inches is the maximum space. That means that 76.2 centimeters is the maximum space. It's the same space. The space has not changed. The only thing that's different is the units that you used to measure it. So if 76.2 is the most we can absolutely fit this bookshelf, then an 80 centimeter bookshelf is not going to work for our needs. Okay, so we're going to go ahead, and that's it for the first topic, which is kind of why I chose it to go in this, this double lesson tonight, because it's so short. But that's basically how it goes, and we are going to go ahead and scroll forward, and we're gonna shift gears. So if you want to take a 5-minute break and just stretch your legs, or shake it off and just kind of change your mindset a little bit, we're gonna change our frame of mind into talking about lines and angles and geometry. That's what we're gonna do right now. So let's go ahead and jump right into lines and angles. The first thing we're going to talk about is, how do you measure an angle? So first, what even is an angle of something? So angles can measure rotation of something from an initial point. So I want you to take your pencil or pen or whatever you're writing with right now, and I want you to set it flat down on the desk in front of you, or wherever you are, enjoying this lovely class right now. Kitchen table, in the car, in the break room at work, whatever you're doing. Lay that writing utensil flat down on your table, and then choose one side, the left side or the right side. Just pick one of the points, right? Grab that pencil, and then only at that point, and then I want you to sort of like lift it up. So the point where your fingers are stays on the ground, and the other side of that writing utensil is kind of changing up into the air. It's rotating into the air. So what you're doing is you're forming an angle between the surface and the writing utensil, okay? That right there, if you can get that concept, the rest of this is going to be cake for you. Um, Another way to explain what angles are or what they measure is they measure the slant or the incline of something. Um, I want you to imagine, how about a seesaw? Okay, think about a seesaw. So you're at a park. Close your eyes. Imagine that park. You're at the park. There's a seesaw, and you and your friend are sitting on opposite sides, right? So the middle of that seesaw is what I want you to think about right now. Okay, how much slant do you have to give that seesaw, right? Before, so like you're going up into the air. You're the one who's going up into the air. The seesaw is moving you upwards. How much slant does that surface need to have before you start to roll forward down, in front, down the seesaw? So that's another important question that we can use, or a real life example we can use to talk about angles. I guarantee you, there is an angle that, once you hit that threshold and go past it and the angle gets bigger and bigger, that, you or any other object or whatever you put on that slanted surface would start to roll forward. I mean, that's due to other issues like gravity and friction and stuff, but the angle is really, that's going to be your tipping point. That's where they get that terminology from. So let's look at some other real life examples. So on our first example here, we have these, lovely construction people, and they all have ladders. And what do you notice about the ladder in all these pictures? It's leaned up against a building, right? So that's leaned up there at an angle. And so I'm going to use my pen here, my pencil, as sort of an example. So this is where the ladder is in this picture, right? So you can see that. What if the ladder, like the base of the ladder, was further out from the wall? Okay, so there's some angles that are changing here, right? The angle that is down. I'm going to zoom this in. The angle down here changes, and the angle up here changes, because if the ladder's placed this way, that's only a certain number of degrees off the wall or a certain number of degrees off the floor. And then if you were to tilt that ladder a little more, then your angle is totally different now, because you'll have an angle where the ladder meets the wall here and an angle where the ladder meets the floor here, and that might be it is a different measurement than the original positioning. So my question to you is, why is that important? Well, the angle of that ladder and the way that it touches the wall is like a safety issue, right? I mean, there is a certain point where if the ladder is too low to the ground, and too far away from the wall, and the angles change it up, then the ladder becomes unsafe, and you no longer can stand on that. It won't support your weight. Okay, there's only particular angles where the ladder will be able to actually support you standing on it and leaning it up against an object. So let's think about a totally different type of example. Here we have a football player. Okay, he's holding a football, and I want you to imagine him throwing that football, right? I could throw it like straight forward. I could go a little bit higher in the air. I could even go like straight up above my head, okay? Or even a little less than straight up above my head. And that's what this is, sort of a diagram of. If I were to go kind of like straight forward, right, the ball is going to go like this. Or if I go a little higher, it might end up going like this. Or even higher than that, and it might end up going like this. So if I draw that way, let me zoom this out a little. Does that sort of help you visualize why the angle at which they throw the ball might make a big difference in terms of how far that ball is going? That is another real life example of angles. And I personally am not really a sports person, so I was very interested to learn that when coaches are giving players directions, like for plays and stuff in the football field, they use angle measures in degrees to explain to them things like this, like what angle you should throw the ball at. and what angle you should be running at to get the best trajectory for you running that ball across the field, or whatever it is. So those are just some real life examples to sort of ground this concept into. And my question about this football player was, if you change the angle of the throw, does that change how far it goes, how high in the air it goes, et cetera, et cetera? And it looks like it does actually make a difference, okay? If you want to experiment, please go outside with some kind of ball or something and check that out. Okay, so back to the actual mathematics and the science behind this. So to get precise measurements of angles, we use a tool that's called a protractor. This is what a protractor looks like right here. So we would put the vertex of our angle right here in the middle point. There's usually a little like a hole in this, so you can see exactly and line it up exactly. And then you look to see, where the two rays end up. So you might have like one that goes this way. If you think back to the example I gave you a moment ago about lifting your writing utensil off the desk, this might be the desk, right? And then if you lifted your pencil up about this far, okay, then that might be the pencil. And the protractor would tell you, starting at 0, how many degrees you just rotated that pencil up into the air, and it looks like that would have been 50 degrees, 50. Now, you might be saying, why does it have measurements, 2 measurements for every point you stop at? And it does because you could go from both sides. Like, you could start your measurement on this side, and then you would count in this direction. But we started on this side, so we're counting from this direction. So we're going to start always at 0. Okay, so that's a protractor. I did find this video for you guys. It's really short. It's like 2 minutes or something. If you wanna click on this, just pull up my PDF version of the notes on your computer and click on this. And I know it's like a kid's video. It is what it is. But it's a really concise, like pretty quick way of explaining what angles are and how the protractor measures them. So you might want to check that out. All right, so I'm going to keep rolling through here. The next thing we're going to be talking about is segments, rays, lines, and angles. And it's going to take us, I think we have like 3 more pages of these notes. These are going to not roll by so quickly because we're going to be drawing some examples here, so we can kind of demo, one thing at a time. So the first thing we're going to talk about is we're going to talk about what a point is. So usually when we're talking about geometry, we're going to have, I just realized you can't see this, so let me scroll that out. Okay, so usually in geometry, we have this grid, which is called a coordinate plane. Today, I'm just using a grid. There's no, there's no point, there's no like numbers or anything on here, but normally there would be like numbers. We're going to be using this grid so that we can really precisely and accurately kind of draw these figures. So the first thing I want to tell you about is something called a point. So if I asked you to pick any point on here, that would be any intersection of these gridded lines, okay? So I'm going to pick this part right here. I'm just going to draw a point, and that's it. That is a point. Now, typically in geometry, what we are doing is we are describing points, we're describing lines, we're describing angles and shapes. And in order to do that effectively and efficiently, we use the letters of the alphabet to label these different parts of all these different figures. So in a point, you would just have like, the letter above it, and that would be point A. That's how you would describe that. Or if you had another point and it had a B above it, that would be point B. So if you ever heard that terminology, I just need a car that gets me from point A to point B, like this is it. This is where that comes from. Here's point A, and you could draw point B somewhere else on here, and that would give you like, 2 different points to measure the distance between, or, whatever. So that is a point. I'm going to do this in red, okay? I'm going to change colors so we can kind of keep track of what's happening on our diagram. Something else you can talk about in terms of geometry is a line. A line is a straight object. It doesn't have any curve or bend to it. It's a straight object, and it continues forever in opposite directions. So you can also have points that are on a line, and you can also have segments of a line. And that's a lot, I know. But let's draw something out. So here is a line. Okay, actually, I think my palm is like zooming the paper. Hold on. So there we go. So that's like the straightest I could get it. Okay, so that's a line. We're calling it a line. Okay. So I know it's a line because I have these arrows on the end that tell me that that line continues left and right, opposite directions, forever and ever and ever. That those arrows are very important. You got to remember the definition of those arrows. So the arrows tell me the line continues. That's forever and ever. Okay? So that's what that arrow means. And I know now this is a line. We're going to use the green to display that. Okay. Now, right now, there's no name for this line. Okay? But what if I asked you to pick some points that were part of or fell on this line? Okay? If you were to do that, right, I'm going to use, I'll use green still. If I told you to pick some points, right, you might pick like, here's a point that's on this line, here's a point that's on this line. Really, all of these are points on this line because all these little intersections here, okay, are points like we talked about before. This is a point. These points exist on this line, okay? So if you labeled these points like A, B, C, all those points are part of this line. And so you can actually use any of them to describe this line. You can say you can name this line using any of the 2 points that are on it. Now the way you would do this, all right, I'm gonna put line first, and I'm just gonna use A, B, okay? So the way you would do this is you would have these 2 arrowed lines that come up on top of the letters. Okay, so what this means, if you were to read this out loud, this right here that I'm pointing to, this would be line AB. And that's how you would know, oh hey, I am talking about this line right here because this is a line and it has points A and B on it. And now you might be wondering, well, can't I use the other points? And you 100% can. Another way to describe this line would be BC. Okay, this also describes this line because points B and C are on here. You could also do AC. And that it describes the same line. All 3 of these terminologies here describe this exact same figure, this line, because these points exist on this line. And I know it's a line because it has the 2 arrows at the end that say it goes on forever and ever and ever. Okay, so the last piece of like this section right here has to do with line segments. So I want you to think about the word segment and what does that mean, because what happens a lot in mathematics is that if we understand the definition of a term, it may be easier for us to remember what it is and how it works. A segment, if you go to the dictionary and look it up, a segment is just a part of something. So think about like a sketch show like Saturday Night Live or Mad TV, right? So in those shows, they have several different segments that they show inside of that 1 hour, hour and a half, or however long it is, okay? Those are segments. If you're watching a movie like on a DVD or a Blu-ray, right, those are often split up into chapters, okay? And a chapter is just a segment of the whole movie. It's just a part of the whole, okay? So we're going to kind of translate segments now into geometry and how a segment can be a part of a line. So I'm going to switch colors. We're going to do this one in blue. We're talking about line segments here. And so here's a line. Oh, I don't know why I just drew that dot. My bad. Okay. So, oh, I know why I did that. Never mind. Never mind. Okay, so here's a line. We're going to do our arrows. Here is a line. Here we go. And on that line, we have point D and point C. Now, if I gave you the abbreviation DC with the arrows above it, we already talked about what that means, and that means that you have a line. This is line DC. That's the entire figure, okay? This is the entire length, the entire line that goes on infinity in both directions. What if I told you DC and I just put a line above it, no arrows? Okay, the big difference here is no arrows above this, right? What this is this is line segment DC. It's just describing, it only describes the distance that happens between point D and point C, okay? And then another example that you could look at is, how about orange? Why not? Is, let's just say you have F and G, and they're connected there. No arrows at all, okay? The only way to describe this would be FG with a line, which is line segment FG. You couldn't describe this as a line, and the reason why is because you don't have the arrows on either side going off into infinity. But you could describe it as a line segment. If I were to go ahead and draw more with the arrows, then you could say it's line FG and it contains line segment FG. So that is basically the rundown of points, lines, and line segments. The next part of this has to do with, I'm going to roll down so we can see it. My page says loading. That's kind of weird because I know there's text on here and on here. Okay, maybe I need to reload. Give me 1 second. Okay, figured it out. My bad, I just had to reload. Okay, so back to our next part. The next part is about rays and angles. So a ray, R-A-Y, we're going to circle this in blue right here. A ray starts at a certain point. Whoops, okay, now you can see that. A ray starts at a certain point, okay? And then it continues on only in one direction forever and ever. So a ray could be, let's say this is point A, and that goes this direction, and it has an arrow, and it goes on forever and ever and ever. That is what a ray is. Okay, so it stops here, S-T-O-P, and here it goes forever. Now the difference, remember, is that in a line, the both sides go on forever. In a line segment, both sides stop at those endpoints. And in a ray, one side stops. That's here at this starting point. It doesn't go any further than this. But out of one direction, it goes on forever. Now, right now, I can't name this ray because I only have 1 point. What I really need to do is I need to pick something else like here and just make this be point B. I need at least 2 points in order to name this figure. So now I can call this AB, but am I going to put like this on top of it? And the answer would be no way, because this would imply this is a line that continues in both directions. It does not. Can I do this one with just the straight line, no arrows? The answer is no, because on one side of this, okay, that's a trick question. So technically, that would be a yes, okay? Line segment AB would just be from A to B, okay? How would I describe the entire figure, though? The ray that is AB, okay? And this is, I'm just going to really spell it out. This is a line segment. Now, how would I talk about the entire figure, which is a ray? Well, I would do AB, because those are my 2 points I have. And then on top of that, I would just go with the arrow on one side. This is ray AB, and it describes the entire figure of ray AB. That is what a ray is. So the symbol makes a difference. The direction of the arrow makes a difference. You couldn't call this AB with an arrow this way. This is wrong because the direction doesn't go from right to left. It goes from left to right. That's where the arrow is heading. That's why that makes a difference. And typically in most things in geometry, we care about the order of the things being from left to right, and so that's just, you should just adopt that mentality and try to always apply that. Okay. The next thing we're going to talk about is angles and how angles are formed when we're just drawing them. So we saw some real life examples. Now we're going to put pen to paper, and we're really going to show you how to do this mathematically, okay? So angles can be formed lots of different ways, right? You can have like 2 lines that cross each other, and then the angles would be here, 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 and here. Those are all angles, right? The way we're going to really approach this to start is we're going to talk about 2 rays that share the same endpoint. That's going to be the easiest way for us to look at this. So let's say we have point B right here, okay? And then above that, we have a ray that kind of goes this direction, and we'll give that a point, and we'll call it A. And then we have another ray that goes this direction, and we'll call that point C, okay? So let's describe the figures that we see here, okay? So we have BA, that would be this ray right here from B to A. And then we also have BC, that's a ray, okay? That goes from B to C, well, B, C, and forever. You could also talk about the line segments. You have BA as a line segment, and you have BC as a line segment. And those pieces would just be from B to A or from B to C. And then the last piece, this is the brand new information here, is how you can explain an angle. The angle that we are talking about is this angle right here. I just drew it in red. It's right here. This is the angle. Okay? And the way you describe this is you use all the points outside, and then this special point right here is called the vertex, and that always goes in the middle. So angles are named by point, vertex, point. So this one could be A, B, C, or it could be CBA, because CBA and ABC, those are the only 2 combinations you could have with those 3 points, where the vertex, B, is in between them. Okay, now you're probably also wondering now, what is this little symbol that I just drew right here, okay? This symbol in front of these letters signifies that it is an angle, okay? You're going to see that a lot going forward, so commit that to memory, okay? This is the angle symbol. So, in other words, this is angle ABC, and this is angle CBA, which actually these 2 things they're describing the same angle. And all these pieces, how we're describing this, is describing the angle inside here, whatever degrees this is. Okay, that is what we are talking about with angles. I think that's it for the angle part. Yeah, it is. Okay. So, actually, let me just leave this up for 1 second. and I want you to like pause the video and like take a deep breath and think about everything I just said about these angles. Let it soak in a little. If you want to rewind a little bit and just rewatch this, make sure you get it. I'm going to have some more activities for you after the notes are over, so it'll kind of really bring this home. But absorb all this right now. Absorb it, okay? All right. So next, I'm going to be talking about something completely different, which is parallel versus perpendicular. This is just vocabulary. That's all this is. So don't be scared about it. Okay. And we're just going to draw some pictures here of what this means. So parallel and perpendicular describe um, they describe lines or line segments basically. So if I were to say something to you about, and this is the way that you're probably going to remember this, if I were to say something to you about two things being parallel, like streets, okay? We all live in this area, right? So what if I was talking about Military Trail and Congress Avenue? Are those parallel streets for the most part? And just go with me on this example because I know, they might have some bend to them, or, one might end before the other one. That doesn't matter. My question is, do they run alongside each other, or does military and Congress ever intersect? So for the most part, I'm pretty sure they never intersect. I'm almost certain of that. I could be wrong. I don't know. But for the most part, they're parallel. So parallel would be like this line and this line. Okay? Okay, and something that we use in geometry to signify that they are parallel is we use these little markings, like with little arrows on them. So these little symbols mean parallel. Because if you think about it, even if you look at just the way I drew these, I don't think these are exactly parallel because I kind of did this one at an angle, which was by accident. For right here, they look like they're parallel, like they're never going to intersect. That's the definition, by the way. They never intersect. But if you kept drawing these, like eventually, I think just the way I drew it, like, see how they're getting kind of closer and closer down here? Like they're eventually going to cross each other. So, you know, it is what it is. I mean, I just kind of drew them really quickly and sloppily. But the saving grace here, the good news, is that because I put these symbols here, you are completely free to presume and assume that they are going to be parallel always and forever. This symbol guarantees that, okay? If you don't have those symbols, then you don't have that proof, all right? That's the gist with parallel. The other type you could have with lines is perpendicular. They intersect each other and form 90-degree angles. So you might have like a straight up and down, and then one that crosses like this. Okay, here's a line, line, line. There's no symbols that I can draw on the lines to tell you that they are perpendicular. However, I can put this little symbol in the corner, and I can actually do it. I can do it on all the sides if I want to. Okay, they're little squares, all right? The little squares signify that they are a 90-degree angle. So if I have two lines that intersect and they form 90-degree angles, then they are perpendicular to each other. That 90-degree angle is going to be the proof for you. If the lines, let me use a different color like orange. Actually, I don't know why this is drawing like this. Get rid of that. Okay. If the lines cross like this, and they don't have these symbols inside the angles here, this is not parallel and not perpendicular. It's neither. I spelled that wrong. I can't even spell my own words. Perpendicular. Okay? The telltale sign here for these special lines is that they either have these symbols and they are next to each other and will never intersect. That's parallel. Or they are perpendicular and they form 90-degree angles when they cross. Or it's neither and it might look like an X or something, or something similar to that. Okay? All right, we have one more page of notes to go. We're going to talk about the angle addition postulate. That's a lot of fancy words, but that's what Essential Ed would like me to tell you about with this geometry is the angle addition postulate. A postulate is just a statement in geometry. Well, really, it doesn't have to necessarily be geometry, but you're going to use it a lot in geometry. A postulate is a statement that we know to be true. Okay, so for example, if I told you, the sky is blue, okay, that's just something that we all accept to be true, right? The sky being blue is just something that it is what it is. I mean, there's science behind why, but who cares? Because we know that the sky is blue. We know that that's true. That's exactly how a postulate works in geometry. So the angle addition postulate says that if two angles have the same vertex and they are side by side, you can add the angle measures of the two smaller angles to get the bigger angle. So, or vice versa. They might give you the big angle and have you find the smaller angle. So I'm going to draw some examples of this. I'm going to do two examples. On the left side here, I'm going to show you, here is a big angle. And we're going to do another one like in the middle of them, okay? So this point right here is the vertex. It's the vertex, if I can highlight this, it is the vertex of this angle right here. And then it's also the vertex of this angle that's formed right here. Okay, so I hope you can see both of those things, all right? So we need to mark these up. So we need to put a letter here. We're just going to call this, I don't know. I need to put points on all of them, right? Because I can't name these rays or name these angles. A, B, C, C, B, A, B. I guess we can put D. That's fine. They're going to be out of alphabetical order, but it's, it is what it is. You can't have it be perfect. Okay, so we have, we're going to be giving you some information. So the first thing that you're going to be told is you are going to be told that this one is some degrees, and it's going to be given information to you, so you don't, you're not going to have to get a protractor out and measure it yourself. Well, maybe you'll have to. I mean, you won't have to in this problem. This is 34 and this one is 45 degrees, okay? So what the angle addition postulate says is that for this type of problem, because these two angles have the same vertex, the measure of angle ABC plus the measure of angle CB and D is going to be equal to the measure of angle ABD. Oh, that's supposed to be a D, not a C. 1 second. D. Fixed. Okay. Now, what is all this saying? Can you translate this terminology? Okay, so first of all, let's think about what's happening here. First, we have a little M, okay? That's brand new. You haven't seen that before. What the M tells you is it just stands for the measure, so in terms of degrees. So the measure of angle ABC, that would be this one right here, ABC, plus the measure of angle CBD, that's this angle right here, equals the measure of angle ABD. That's the whole thing, this big angle formed by the two outside rays. All this is saying is that if you add these two together, you get the whole measure of this whole thing. Okay, that's the really boiled down way. So 34 degrees plus 45 degrees equals the measure of angle A, B, and D, ABD. So we need to add that together. We're going to get 79 degrees, right? 5, 9, 3, and 7. Yeah, 79. So the measure of angle A, B, and D is 79 degrees. And I got that by adding these together. That is the angle addition postulate, okay? Another example, another way you might see this problem asked, okay, is you might have your big angle right here, and it's cut in half this way. Not half exactly, but there's a ray that goes through it. We're going to label this whole thing. We're going to call this F, G, H, and I. Okay. And you're going to be given the measure of angle FGI is 100 degrees. Okay, that's important. The measure of FGI is 100 degrees. The measure of FGI, this entire thing here, this entire angle, all of this is going to be 100. That means, because of the angle addition postulate, that means this angle and this angle added together need to make 100 degrees, okay? Now, and I also need to tell you that the measure of angle HGI is 49 degrees. So that means we know that this is 49 degrees right here. What is this one? What is the measure of angle FGH? That would be FGH, this angle right here, okay? Now, you might be saying, like, you're really dragging this out, and I'm not trying to drag it out. I just want to make sure it's really clear how you do this. But if you have the entire thing is 100 and one of them is 49, what's the other half have to be? It has to be 51. And you can do this mathematically by saying that the measure of FGH plus the measure of HGI equals the measure of FGI. I'm doing angle addition postulate here to really draw out and explain that the measure of this angle right here, let's highlight it, this angle here, and the measure of this angle in here has to be equal to the measure of the whole big angle right here. And when we work this out mathematically, what we end up learning is that we don't know FGH, so something plus HGI is 49 degrees equals the whole thing, which they told us was 100 degrees in the problem. So the measure of FGH, which we did not know, is 51 degrees. That, my friends, is the end of this lesson. We have done and covered everything that we need to do. I am going to next create some flashcards for you guys because there were a lot of vocab terms in this section, and I'm just going to post that link for you on Google Classroom so you can kind of consume that at your own pace. I'm going to use a service called Quizlet for that. If you've used Quizlet before, great. If you haven't, don't worry. It's real easy to use. And then I think there might be a Delta Math that goes with this. I've got to look and see what they have available. But if there is one, then you will see it in there, and I will post that on Google Classroom for you to see as well. Okay, guys, I hope you had a fun, enjoyable lesson tonight, and tune in tomorrow for our next two topics. See you later. Bye-bye.